The Navier-Stokes equations govern the flow of incompressible fluids, like water. A $1 million Millennium Prize rests on a single question. If you start with a completely smooth velocity field of water, can the fluid ever concentrate its kinetic energy so much that its velocity becomes mathematically infinite? In mathematical physics, this theoretical point is a finite time blowup, or a singularity. It represents a state where the amplitude of the waves becomes so great that the standard equations of motion are no longer applicable. Everyday experience suggests water is stable. It splashes in a bathtub and then settles. But mathematicians require a formal guarantee that no microscopic conspiracy of colliding particles could ever trigger an explosion of infinite velocity. Fields medalist Terence Tao attacked this problem by stepping outside the strict rules of physics. He chose to artificially average the equations, essentially changing the laws of mathematics to see if he could force a singularity to occur. Proving global regularity, the guarantee that a fluid stays smooth, requires a structural audit of the equation's mathematical boundaries to find the exact point where its internal logic fails. This grid illustrates the constant tug-of-war within the Navier-Stokes equations. Linear dissipation, shown in blue, uses viscosity to calm the fluid. Nonlinear transport, shown in red, uses the fluid's own motion to push energy into new locations. In 3 dimensions, these equations are supercritical. As you move to smaller scales, the destabilizing transport forces become overwhelmingly stronger than the viscous damping. In many physical systems, you can use a simple average to predict behavior, but statistical tools like the central limit theorem fail when the microscopic forces are this highly correlated and nonlinear. This supercriticality is why weather models struggle to predict patterns past 2 weeks. The microscopic information is too important. It amplifies so quickly that broad macroscopic averages can't capture the change. Because the equations are supercritical, mathematicians cannot rely on bulk assumptions. They must track exactly how energy transfers through every individual microscopic eddy to see if a blowup is possible. The most direct way to engineer a blowup is to force a cascade. You take kinetic energy from a large macroscopic eddy and push it into a smaller microscopic eddy as fast as possible. In a 3-dimensional fluid, this energy smears out across multiple scales simultaneously. It fails to stay concentrated in the smaller eddy during the transfer. This dispersion gives the fluid's natural viscosity a larger surface area to work with. The energy is spread too thin to trigger a singularity, allowing the viscosity to damp out the motion. Tao bypassed this by engineering a cheat. He created an averaged Navier-Stokes equation that selectively turns off the specific energy channels responsible for this dispersion. Successfully engineering a singularity requires absolute control over the flow of energy, which means overriding the natural physics that would otherwise spread it out. With dispersion removed, Tao needed to move energy across scales without losing its concentration. He solved this by programming a delay into the fluid's math, creating a series of airlocks. The energy is held at a larger scale until the container is at 100% capacity. Only then does the gate open, instantly flushing all the kinetic energy into the next microscopic scale. This forced delay keeps the energy strictly localized at one scale at a time. It inches forward in concentrated pulses, making it impossible for viscosity to calm the fluid down. These gates function as basic logic components. By stacking them to regulate energy levels and flow rates, Tao's model creates mathematical analogs for resistors and capacitors, effectively building a circuit where pressure and kinetic energy take the place of electric current. By imposing these strict delays and gates, the continuous physical substance of a fluid is transformed into a discrete architecture capable of carrying signals. If you take isolated fluid pulses, like vortex rings, and fire them at one another, their collisions produce predictable outputs based on input directions. These predictable collisions are the physical basis for Boolean logic. A setup where 2 inputs collide to yield a specific output trajectory acts as an AND gate, while a single input acts as an OR gate. This mirrors the behavior of cellular automata. In Conway's game of life, simple localized rules generate glider guns and functional logic gates that can be linked together into a larger system. Once a system can reliably execute AND and OR gates, it achieves Turing completeness. This means the system is capable of running any computable algorithm. Within the boundaries of this averaged equation, the physics governing the fluid have been turned into a system capable of executing software. To force the final blowup, Tau programmed a von Neumann self-replicating machine into the fluid. Its only instruction is to build an identical copy of itself. The massive fluid circuit assembles a smaller replica in a dormant state. It then transfers all its kinetic energy into that replica and powers down. Because of the equation's scaling symmetry, the smaller replica runs its replication cycle much faster than its parent. Each generation is geometrically smaller and executes its code more quickly. As the scale of the fluid computer approaches zero, execution speed reaches infinity. All kinetic energy concentrates into a single zero-dimensional point. This accelerating computational recursion achieves what natural physics resists. It successfully programs a finite-time blowup into the fluid. This proof doesn't mean the water in a bathtub is a computer. It proves that an idealized averaged fluid equation is physically capable of supporting universal computation. In mathematics, this construct is an obstruction. It serves as a permanent roadblock for anyone trying to prove that a blowup is impossible. Any proof attempting to show the true Navier-Stokes equations are safe cannot rely on rules the averaged equation also follows. The mandate for mathematicians is now clear. To win the Millennium Prize, they must isolate the exact physical feature in the true equations that actively prevents this kind of computation. By building a fluid computer, Tau has permanently narrowed the search, ruling out any generalized theories that ignore the microscale complexity of the fluid. This approach maps fluid dynamics and turbulence directly onto Turing machines and software loops. Mathematical modeling uncovers the hidden architecture of the universe by allowing researchers to test versions of reality that aren't possible in our own. While science collects data to refine its models, mathematics follows its axioms to their furthest conclusions, exploring theoretical extremes until it reaches a definitive proof. Understanding the hardest limits of our reality requires moving past physical intuition and following the abstract requirements of computation.